My name is Eric Turner, and I'll be discussing Lab 1, which involves tape and electricity. To begin, introduction and background. Everyday objects acquire excess charge via interactions with other objects, whether it be neutral or charged. Like charges will always repel, and opposite charges will always attract, and we'll sometimes find that these forces can overcome or balance out other forces, which we'll discuss later in the lab. A few of the laws and equations that we'll have to make use of in this lab include Coulomb's law and Newton's second law. So, in the beginning of the lab, when we're first trying to find out, one, the charge on each tape, whether it's positive or negative, as well as if it would attract or repel the other charge, we were asked to make expectations and then record our observations. My expectation for one was that the tapes would repel, and that's confirmed. And from that, we can assume that they are the same charge. Expectation two was that they would hold positive charges. I also found that to be true. And from that, we gained the knowledge that it would be attracted to negative charges. So some of the critical assumptions and approximations we have to make when using calculations for this lab. You have to assume that the charged tape will act as a point charge with charge located at the center of the tape. You also have to assume that the charge on the tape is uniformly distributed and that each tape has approximately the same charge. We can also ignore air resistance of the moving tape. So some of the data I recorded, and a picture to the left states some of the math that I had to do to get to these numbers. I found that the length of tape B was 0.2032 meters, and that the force on gravity of tape B was 0.001991 newtons. I've recorded that the separation distance between the two tapes when you brought them near was 0.015 meters, and then the real number that we were looking for, which is the charge on tape B, I found that to be 7.0 times 10 to the negative 9 coulombs. And to the left, you'll see the calculations for fraction of atoms with excess charge. You'll see in the first line, I found the surface area of the tape, and in the second line, I found the cross-sectional area of each individual atom. And then dividing those two numbers, we were able to find the total number of atoms on the piece of tape. And using that in the denominator and the total number of electrons we found in step 4, you can find the fraction with excess charge. So my computational model, I have a blue sphere for tape B and a green sphere for tape A. My green arrow denotes the gravitational force, and my blue arrow denotes the electrical force on B from tape A. And you'll see that the blue and green arrows are equal, and that's critical when you examine Newton's second law, F equals ma. That assumption and ideal is what allowed us to set the electric force equal to the gravitational force and therefore have the power to solve for charge. And then here you'll see my code. It's pretty simple. I used the function from lab 0 to find the electric field created by each tape. And then using that and the electric force that we found by setting equal to the gravitational force, you can then find the charge. Some of the critical questions we need to ask ourselves. What if electrons had positive charge and protons had negative charge? You'd think that'd change a lot, but in reality, it wouldn't. Like charges would still repel and opposite charges would still attract. None of the observations in this lab would change. Why is it important to handle the charged tapes as little as possible? This is important because, as we described earlier, interactions between objects often will affect the charge on them. So by limiting the amount of contact we have with the tape before the experiment, we'll guarantee that we have more charge on the tape. In summary, all objects, charged or otherwise, are subject to electrical interactions, whether it be rubbing, pulling, any kind of interaction between the two. And we can also make by making some assumptions, you can easily estimate the amount of charge on an object and field it produces.